The descent of an ore elevator in a deep underground mine is not a violent fall. It's a controlled dance of gravity, mass, and precision. Every ton of mineral is balanced by counterweights. Every vibration absorbed by shock systems calibrated down to the millimeter. Now imagine applying that same logic, not to stone, but to something infinitely more delicate. 5 million tons of lamb carcasses, exported annually across oceans and continents. What connects these two worlds, the crushing depths of the earth and the cold chain of food logistics, is not just machinery. It's the principle of engineering stability under pressure. Transporting lamb meat at industrial scale is not simply about cold temperatures. It's about how that cold is distributed, preserved, and shielded from interruption at every stage of movement. Like in mining, the core challenge is vertical integrity, managing how mass responds to movement. In this case, that mass is biological. Carcasses that must hold their shape, internal structure, and cellular moisture over thousands of kilometers. That's where the analogy deepens. Because just as ore can crack under uncontrolled descent, lamb meat can suffer invisible structural damage when thermal gradients or torque exceed thresholds. A tiny rise in core temperature, just 0.5 degrees C, during a container transfer or loading pause, doesn't just warm the product. It silently erodes shelf life by up to 12 hours, accelerating degradation before it even arrives. This is why modern lamb logistics now mirror some of the smartest engineering from mining lifts. Freight trailers are no longer simple boxes. They're modular environments. Inside, the meat is stratified in layers that balance load weight, just like counterweights in a shaft. Vibration-dampening joints absorb road oscillations to prevent torque-induced shear, a force that would otherwise fatigue the meat's muscle fibers and reduce texture quality. Even airflow systems operate like thermal shields, managing the inertia of cold. Because what matters in both cases, mining and meat, is not just getting to the surface or the destination. It's doing so while preserving internal stability. What we're witnessing is not a coincidence of methods, but a convergence of needs. Mining elevators taught us how to stabilize tons of fragile mass under motion. Lamb export logistics have adapted those same principles to preserve a biological product that's equally susceptible to pressure, vibration, and thermal shock. One deals with rock, the other with flesh. But in both, what's at stake is value. Value that depends entirely on maintaining structure, timing, and temperature. And so behind every lamb rack on a restaurant table, behind every vacuum-sealed cut in a supermarket freezer, there's a logistical ballet that began long before, not on a plate, but in a moving chamber engineered like a mine shaft. A space where meat descends not into the earth, but into a global system built to preserve it. Perfectly chilled, perfectly timed, and perfectly still. But temperature is just one layer of this choreography. There's a second force at play. Silent, invisible, and just as damaging, moisture. And when it's left unchecked, refrigeration alone won't save the cargo. Inside a perfectly chilled shipping container, everything can seem under control. The temperature gauges read steady, airflow systems are humming quietly, and the meat appears pristine. But something invisible is already at work. A microscopic layer of moisture forming across the surface of each lamb carcass, born from the proteins that begin to perspire the moment external humidity meets internal cold. These aren't droplets, they're condensation nodes, tiny points of imbalance that, over thousands of kilometers, can compromise the entire load. This is the flaw in traditional cold chain logic. Refrigeration does not equal preservation. Cold slows decay, but it doesn't regulate vapor. As meat travels in tightly packed units, the thin film of moisture on its surface begins to shift with the internal airflow. If not managed, this vapor accumulates in pockets, settles, and drips back onto the meat. And that is the beginning of what refrigeration alone cannot prevent: surface mold, microbial blooms, and texture degradation. To solve this, engineers introduced a solution borrowed from moisture control technologies in aerospace storage: hygroscopic polymer panels. These panels, installed along the ceilings of containers, function as silent regulators. They don't circulate or cool, they absorb. As vapor rises inside the container, these polymers capture excess humidity and lock it in, preventing it from falling back onto the carcasses. There are no moving parts, no complex mechanisms, just a continuous passive system working in tandem with cold air, turning invisible risk into manageable equilibrium. The results are measurable. Containers that maintained a relative humidity just 1.5% lower than the standard, thanks to ceiling-mounted polymers, showed an 18% reduction in microbial surface growth. That number matters. It's the difference between meat that must be retreated and meat that arrives inspection-ready. One cooperative in southern Chile took this principle further. By integrating humidity control across its entire export fleet, it cut end-of-journey mold treatments by 72%, reducing monthly reprocessing costs by more than $45,000. Not through more refrigeration, not through faster shipping, but through smarter environmental design. Moisture in this context behaves like thermal energy. It spreads, it settles, it transforms. And like heat, it must be managed not by reaction, but by anticipation. That's why today, in high-efficiency lamb transport, controlling humidity is treated with the same priority as controlling cold, because one without the other is an incomplete defense. In the words of a logistics coordinator behind one of these upgraded systems, in lamb transport, moisture is the unseen heat. Control it like you'd control temperature. And when that's understood, the container becomes more than a cold box. It becomes a sealed ecosystem, tuned to preserve not just meat, but everything its quality depends on. But even in a perfectly controlled atmosphere, another variable threatens that integrity: geometry. The way the meat is suspended, the angles it assumes, the balance it keeps under motion, all of it defines how cold behaves across the body of each carcass. And it's this spatial choreography that will shape what comes next. Cold air is not neutral. It moves, it falls, it wraps itself around objects, but only if space allows it. Inside a refrigerated container, the distribution of that cold is shaped not just by fans and sensors, but by the physical position of the product itself. And when the product is a suspended lamb carcass, weight, tilt, and posture become the hidden variables that determine whether the cold does its job or not. The way a carcass is hung, at what angle, at what height, and with what spacing, affects how blood drains post-slaughter, how quickly the core temperature drops, and how evenly that temperature holds throughout the journey. This is not aesthetic, it's biochemical. When posture prevents proper drainage, residual blood creates microenvironments that slow chilling. And that delay opens a window for enzymatic activity, leading to dark spots, cold burns, and localized spoilage, especially in the thoracic regions. To counter this, engineers developed modular suspension racks with embedded sensors and actuators. These racks don't just hold the carcasses, they respond to terrain. When the truck climbs or descends, when it banks through curves or moves across uneven surfaces, the rack system adjusts in real time, altering the tilt of each suspended lamb to maintain optimal drainage and airflow contact. It's kinetic stabilization applied to perishable cargo, a logic borrowed from aerospace gimbal platforms and adapted to livestock logistics. The benefits are visible. In a comparative analysis conducted by logistics firms in New Zealand, containers with static suspension systems showed a 14% higher incidence of discoloration and cold burn in the upper thoracic zone of lamb carcasses. These aren't just cosmetic issues. Discoloration lowers grade classification, reduces market value, and often leads to partial reprocessing or rejection, a loss compounded over every ton shipped. In contrast, shipments using tilt-responsive suspension not only preserved visual quality, but maintained tighter chilling curves, with fewer temperature excursions at critical points in transit. An Argentinian exporter adopted the system across its primary European routes. Within 6 months, their shipments showed a 24% improvement in visual grade compliance at EU border inspections. That figure translated into faster clearance times, reduced cold chain interruptions, and a measurable increase in accepted product volume, not by adding refrigeration or speeding transport, but by rethinking how the meat was positioned within its mobile environment. Because in cold chain logistics, geometry is not passive. It defines how temperature acts, how fluids behave, and how biological tissue resists degradation. When meat is aligned with airflow, with gravitational drainage, and with mechanical stability, it doesn't just travel better. It preserves its market value. As one logistics analyst noted, with no metaphor, no drama, just precision. Meat grade is not defined by quality alone. It's the geometry of cooling that seals the deal. And once posture becomes part of the process, the container becomes not just a space of transport, but a chamber of precision, where cold, form, and structure work as one. But even with perfect posture, perfect cold, and perfect humidity, there's still another layer, one that starts not with meat, but with the machines in the field that inspired this entire evolution. Machines that spread fertilizer, grain by grain, with more intelligence than most people imagine. And it's in that pattern, the choreography of adaptation, that lamb logistics find their final lesson. On a dry morning in western Brazil, a fertilizer spreader crosses the edge of a soybean field. It doesn't drive in straight lines by guesswork. It calculates. Inside its system, sensors collect wind speed, ambient humidity, granule density, and topographic inclination. Every second, it updates its release rate, adjusting the force, angle, and timing of dispersion. It's not improvisation. It's precision at scale, a machine capable of distributing nutrients over a 30-meter swath while correcting for the invisible variables of the environment, so that every gram of fertilizer lands exactly where it will be absorbed best. This level of fine-tuned adaptation might seem distant from the world of lamb exports, but the logic is identical. When shipping perishable cargo like meat, the goal isn't merely to maintain cold. It's to respond, moment by moment, to everything that threatens stability. Temperature, humidity, time, vibration. Just like in the field, where a slight change in wind alters the fertilizer pattern, a small external shift during transport can redefine the entire internal climate of a shipping container. And it's here that a new frontier in agro-logistics has emerged. In Denmark, a country known for both agricultural efficiency and maritime shipping leadership, engineers have integrated predictive AI systems into lamb export chains. These systems draw data from multiple sources simultaneously: thermal sensors inside the containers, real-time weather stations along the route, satellite-based ocean current forecasts, and port congestion maps. The result is a dynamic orchestration, where airflow speeds, humidity extraction, and even micro-route adjustments are no longer pre-programmed, but recalculated continuously, based on evolving transit conditions. For example, if a vessel crosses into a warmer marine corridor, the AI reduces internal air recirculation lag to prevent condensation inside the container. If external humidity begins to fall, the system slows the operation of vapor absorption panels to avoid overdrying. Even port delays are anticipated. When a docking weight exceeds a threshold, container settings are automatically adapted to lower energy consumption without compromising the core thermal profile. The container is no longer just a passive cold space. It becomes an intelligent biome, adapting to external physics in order to maintain biological value. The results speak for themselves. On average, shipments using this system reduced spoilage rates from 4.1% to 1.3% across a fiscal year. That difference isn't abstract. It translates into hundreds of tons of meat arriving at peak quality, untouched by frost damage, bacterial bloom, or visual degradation. Not because they were shipped faster, but because every step of the journey was treated as a variable worth managing. This is the future of long-haul meat logistics. Not static solutions, but systems that adapt. Not reactive measures, but predictive correction. And in this, lamb transport borrows from the best examples in agriculture, where machines no longer just execute, but interpret. The way a spreader reads soil texture to optimize nutrient dispersion, a container now reads environmental drift to optimize product stability. It's the same principle, applied to different forms. Because transporting lamb is no longer just about keeping it cold. It's about engineering a journey across oceans and time zones, where the product's integrity must be defended from vibration, moisture imbalance, thermal fluctuation, and atmospheric shifts. And that defense isn't waged by chance. It's designed, with algorithms, sensors, and systems that understand what's at stake. We don't move meat from point A to point B. We orchestrate its survival across physics and entropy. It's logistics with the mind of an agronomist and the precision of a laboratory. The result isn't just food. It's a triumph of design, invisible, continuous, and essential.